Lombardi. I'm a researcher at CNR, Institute, and I'm part of the group of quantum nanophotonics led by Costanza Toninelli in Florence. So, like for most of you, basically, due to the pandemic, our programs changed a lot in the last 6 months. So to be honest, I would have changed the title of my talk to like single molecule for quantum sensing and metrology. That, by the way, also fit better the session in which my talk is. Okay? So let me start to speak about why molecules. So the fundamental reason is that despite we have nowadays very good single sources now, for instance, by semiconductor platform, okay, they still face two main issues. The fundamental one is scalability. So we have a bunch of single photons working really at the same frequency, maybe in the same chip. And also there is still a relevant issue related to interfacing source and optical circuit for manipulation. Indeed, integrated optics and photonics related to manipulation of light and detection is ready for the quantum optical-based quantum technology revolution. The only stage which limits and slows down the revolution is indeed the single photon generation stage. Because of that, we are convinced that some help can be given by a different approach, a complementary platform based on organic dye molecules, which are very famous for super resolution imaging, for instance, also for being very bright, but photo bleach after a while. Actually, this is not all the story, and indeed for specific guest host systems, actually they look very interesting also as quantum system for quantum optics. They show very high brightness, both at room and at low temperature, and fluorescence quantum yield very high, close to 1, and also a high branching ratio in the transition, which is able to provide very narrow photons down to the Fourier limit. That means indistinguishable photons. On the other hand, we can take advantage of the flexibility and tunability of the chemistry and synthesis. For instance, we have access to mass production of nominally identical molecules at low cost. This means that it's like if you can start with a epitaxial quantum dot that are all exactly the same. That does not mean that the scalability problem is solved, because of course the emission frequency depends also on the environment around each quantum system, but so mitigate the problem. So we can start from a simpler stage. So in particular, in my group, we work with the benzotoluene dye molecules hosted in anthracene. And as you can see, in our system is quite easy, and we can routinely provide very high purity single photon states, both in continuous wave and in pulsed excitation, as you can see. And these are almost the same both at room and low temperature. Then also at low temperature, we have verified that the system really have a long coherence time of the electronic transition, as it's seen by the very the coherence time of the Rabi oscillation on the right, that is really close to the theoretical limit for the system. Moreover, we have also verified that the emission in the zero phonon line is really indistinguishable. For the moment, only in continuous wave excitation, but we are in plan to work also and to read out and verify the indistinguishability for parts. So this is a good system. Why there is not many applications and many groups working on this? Basically, the fundamental issue that we missed up to now a photonic platform and fabrication technique to implement and to integrate such quantum emitters in optical and photonic circuits. Because of that, in my group, in the last years, we work in order to have to develop a protocol and have our emitters in nanocrystal, which a controllable concentration of emitters, down to having a single quantum emitter per nanocrystal. This now it's done, and we have it. And also, what we are proud and what is really relevant is that such submicrometric system can provide optical emission without spoiled properties, because this is the main problem when you go to narrow system and small system, smaller than the wavelength. A normal issue is that the quantum properties of the quantum emitters are spoiled. Here you can see, for instance, that we have very nice photostability and no frequency drifting. So now, why we made this nanocrystal? Because this is the simplest way to integrate an hybrid platform with into complex devices. Okay, so you can have you can technique or having a effective deterministic positioning by using a sacrificial mask, or even merge the emitters with materials where which then you can sculpt out photonic devices. Okay. Okay. On this sense, we have worked in two directions. Our nanocrystal. On one hand, we work to have nice single photon sources, and also we work on the field of sensing. The second case, for sensing, we mainly focus attention on into a collaboration with IFO in the group at IFO. Okay, the first experiment we carried out was a very simple one, in which we placed our crystals and with emitters just on top of a graph. This way we were able to detect the fret-like quenching effect would end up in a quenching of the emission. So monitoring the brightness and the lifetime of molecules, or a statistical distribution of molecules closer and farther to the graphene flake, we were able to read out the general statement of the universal theory for that, which states that the quenching strength have to go as the distance to the power -2. And now that we can really position the emitters into complex devices, we have an ambitious project with them, that is to have graphene suspended over pre-selected okay, so that with the capacitor geometry and applying the voltage, you can change and twist the distance within the molecule and the flake. And this way we should be able to read the Casimir-Polder effect as a shift of the emission frequency of the molecule, and also maybe having to read the interplay, the effect of the interplay between the two quantum systems, and also read some back action on the mechanical system. Also, again with them, what we did also was a similar geometry, but simpler, in which we used the graphene and also molybdenum disulfide as a transparent electrode to tune by Stark shift the emission frequency of the molecules. We got a tuning system which is able to tune the frequency up to 10 to the power 4 the natural line width of the emitter, which is quite a lot. Also, with very similar system, now we have been proven to use the molecule conversely to read the charge migration and trap states that you can have in graphene flake, so that to study basically the limits and the properties of graphene flakes. So on the other side, we had also experiments on the field. Okay, so in this, what we have worked on is the development and verification of fabrication technique based on direct laser writing. Provide all organic platform, photonic platform, in which the pre-selected molecule and crystal are embedded in polymeric 3D. Okay, so the system is again very simple, the procedure. So you disperse our crystals within a polymeric drop. Okay, then by direct laser writing, you you carve the photonic structure around the emitter. And preliminary results are in this paper that you can see here on the right. And basically in this paper, we demonstrate two generic structures like suspended waveguides with the form of arcs, and also a sort of seal for collecting in free space. The main, so in particular for the second device, we have demonstrated that we could really improve the collection efficiency by more than 1 order of magnitude, reaching counts at detectors higher than, and also we can demonstrate up to 50% quite relevant for also quantum technology application and metrology. But the main point of the paper actually is the demonstration that this fabrication technique does not spoil the optical properties of the emitter. Indeed, we still have, we keep the high purity and almost Fourier limited line width of the line. And also, we have not spectral diffusion as it is the reference. Okay. Well, going on, what is relevant and what is asked by metrological institutes and also third parts is maybe a single photon source that works, of course, but maybe not so super high performances, but that is a system that is simple enough to exit the quantum optics laboratories and go out, and that can be sold and used in lower level laboratories and companies. Okay, of course, such a device will be very useful for all the fields consuming quantum technologies like metrology, sensing, and communication. In this respect, what we did was to work to a very simplified system. Just position our
2 minutes
on top of a gold mirror, okay? And because we are convinced, and by theoretical calculation, that however, even with this simple system, we can collect out of a cryostat up to 25% of the emission. Also, this system is very simple, so that in a single sample, you can have many emitters that works properly enough. Okay, so we have characterized this in terms of spectrum of the emission, photon flux, and purity, and we end up in collaboration with the PTB within Cyprus. That is a project in order to have single photon sources as new standard. We end up with a paper in which we demonstrate the calibration of a single photon detector against an analog photodiode, which is actually traceable to the primary standard for optical standard flux. Okay, so in this respect, what we did was basically to add the new ring for the traceability chain, going down to lower and lower power flux. Okay, so end up, I want to show our last results that are very relevant in respect to scalability of the single photon. Because within our project, but basically working on the very same system as the one before, we have discovered that actually we have a powerful tool to shift the emission frequency of our molecules. Okay, that is basically is based on the shining light on the crystal in such a way that you generate some charge, some free charge that then is kept in a charge separated state for a while. But the matter is that this while is on the day scale. Okay, so you can really shine the crystal, move the wavelength of emission, and then you have plenty of time to make experiment in which the molecule will emit at the frequency where you leave it. Okay, and this really we have verified that the tuning range is at least up to half a nanometer shift. That is a lot, and make it really useful to match some photonic resonance. Okay, so this really let us envision a chip where we have a number of emitters that will emit really at the same frequency and which match really the some photonic resonance. Okay, this is what we demonstrate in this paper that will be soon in ACS Nano. We had 5 molecules, not far away, of course, from one to the other in emission, but within a wide field of view. And what we had then, we had all of them emitting almost at the very same frequency, as you can see. So dashed, you see the starting position, and then at the end of the shifting procedure, we have all of them almost within a natural line. This mechanism is very powerful as an outlook, because you can have, of course, molecule matching matching a cavity resonance, or have many molecules which interplay with each other. Also, it can be useful for nonlinear frequency conversion on chip. Okay, thank you. This is the end of my talk.